Okay, we're going to be going over numbers 12, hopefully um, through the rest of the review. Okay, mileage tests were conducted on random samples of 100 newly developed automobile tires. The sample mean tread wear was 50,000 miles, with a population standard deviation of 3,500 miles. What is the best estimate for average tread life in miles for the entire population of these tires? So we get several statistics here. We've got 35,000 miles for the population parameter standard deviation. It was a sample of 100, and the mean tread wear was 50,000 miles. Now let's look at the question and make sure that we're answering the right question. What is the best estimate for the average tread life in miles of the entire population of these tires? So just answering that question, could 35 be the best estimate for the average tread life in miles for the entire population of these tires? No, there's no way. 35, 500, 3,500. No, this is the standard deviation. The only possible answer that's even remotely reasonable is 50,000. 50,000 is the average tread life of the sample, and so you use a point estimate to say we're going to use the sample as the population mean. Okay, so 50,000 is the correct answer. So even if there was an option for 53,500 or 46,500, the answer would still be 50,000, because when you have a sample mean, you can use that as a population parameter as a point estimate. And the point estimate right here, let's see here, point estimate, the statistic computed from a sample information to estimate the population parameter. The Office of Student Services at a large Western state university maintains information on the study habits of its full-time students. Their studies indicate that the mean amount of time undergraduate students study per week is 20 hours. The hours studied follow the normal distribution with a population standard deviation of 6 hours. Suppose we select a random sample of 144 current students. Okay, so we've got 20 hours for the standard, or for the mean. Then we've got 144 students. What's the probability of this mean sample is less than 19.25 hours? So we're going to, let's see here. Let's zoom in here. We're going to calculate a z-value. So the z-value equals 19.25 minus 20 over the standard deviation. Let's see, the standard deviation is 6 hours divided by the square root of 144. Okay, because that's the total number of students. And we can use the z-value because we've got the population standard deviation. If we have the population standard deviation, we can use the z-value. 19.25 minus 20, so you got 0.75, or negative 0.75, and then 6 divided by 12, or 0.5. So negative 0.75. So this gives us a z-value of negative 1.5. That's the z-value. So we look at the z-chart, and we are the question is, what is the probability that the mean sample is less than 19.25 hours? So you find, where would the score of negative 1.5 be? It'd be right about here. So what's the probability of a score being at negative 1.5 or below? So this is the appropriate chart to use. Negative 1.5 or below. So we find negative 1.5, and the answer is 0.0668. 0.0668. So the answer is C. Okay. The other chart, if you let's see here. If you look at the z-score for 1.5, it will tell you the probability of it being between negative 1.5 and the mean. That's not what we're asking for. We're asking for 1.5 and below. Okay, so just make sure you know why you're using which z-chart. Okay, next, the intelligence quotient IQ test score for an adult are normally distributed with a population mean of 100 and a population standard deviation of 15. What's the probability we could set a selected sample of 50 adults and find the mean sample between 95 and 105? Okay, once again, we're going to calculate some z-scores. Okay, so we've got x bar minus mu. So let's start with 95 minus 100 over 15, because it's a standard deviation of 15, divided by the square root of 50, because the sample size is 50. Okay, and so that equals negative 5, and then 15 divided by the square root of 50. Let's see here. Let's get the calculator up. So we've got 15 divided by which is, so 15 divided by the square root of 50, which is 7.071. So we'll do 7.071. So negative 5 divided by 7.071. 7.071. And that gives us negative 7.071 is actually 2.12. Okay, so I'm going to erase this. Okay, and let's draw this 2.1213. And so we've got 5 negative divided by 2.1213 equals negative 2.357. So we find the z-score of negative 2.357, and the question is what's the probability of a sample being of 50 adults being between 95 and 105? So right here is going to be where 100 would be. Okay, 100 is the mean, and then you're going to find 95 right here, and you're going to find 105 over here. And what's the probability of an individual or of a sample being between these 2 points right here? So you're going to find the probability of a sample being between 95 and 100, and you're going to add it to the probability of a sample being between 100 and 105. Okay, so the probability using this particular table of a sample being between 95 and 100, you find negative 2.3, and then we go down to 7.5, and it's going to be 0.4912, because you can take the average of these two. 0.4912. So that's the probability of it being between 95 and 100. And also the distance between 100 and 105 is the exact same distance as between 100 and 95. So you can literally just multiply it by 2. So we've got 0.4912 times 2 equals, you can see, 98.24, or you're going to do the one that's closest to it. 98.18. So there's some missing values. Obviously, the chart only goes to a certain point. So if you get something that's really close, the odds are that it's probably going to be the correct answer. Okay, so there might just be some issues with rounding. Okay, so moving on to question number 15. The tread life of tires mounted on a light-duty truck follows a normal probability distribution with a population mean of 60,000 and a population standard deviation of 4,000. Okay. Suppose we select a sample of 40 tires and use a simulator to determine the tread life. What is the likelihood of finding a sample mean between 59,000 and 60,950? Okay, so we have the population standard deviation of 4,000, which means that we can use the z-scores. Okay, so we've got x bar, which we're going to do 59,050, and then we can also do 60,950 minus 60,000 minus 60,000 over, and once again we're using the same exact z-score formula. We're going to be using this z-score formula over and over again. Okay, so we've got the standard deviation, the population standard deviation of 4,000, divided by the square root of how many samples? How many are in the sample? There's 40. And then once again, which if you work all of this out, it's going to give you z-scores of negative 1.5, and the other one is going to be positive 1.5. And so the question is what is the probability of of finding the sample mean between 59,050 and 60,950. So you've got negative 1.5 and 1.5. So once again, it's the exact same distance between. So are you trying to find what's on the outside, or are you trying to find what's in between? You're trying to find what is between 1.5 and negative 1.5. So you're going to find you're going to find 1.5. 4.332 is the probability of it being between negative 1.5 and the mean, and then also 0.332 is the probability of it being between the mean and 1.5. And so you just multiply 4.332 by 2, which gives you B, which is 0.8664. So moving on to question number 16. A university surveyed recent graduates of the English department for their starting salaries. 400 graduates returned surveys. The average salary was $25,000 with a standard deviation of 2,500. Okay. So what is the best point estimate? They even give you the term. What is the best point estimate of population mean? The average salary, in other words, the mean salary, was $25,000. We're using a point estimate. We're taking the sample salary and we're making it into the point estimate, which gives us a $25,000. A university surveyed recent graduates of the English department for the starting salaries. 400 graduates returned the survey. The average salary was $25,000. Okay. The population standard deviation was 2,500 and 95% confidence interval is constructed. What does the confidence interval actually mean? So the population mean is the interval. That's not correct. The population mean is not the interval. That's not correct, really. And then the likelihood... that's not what it's actually saying, is what I'm saying. The likelihood that any confidence interval based on a sample of 400 graduates will contain the population mean is 0.95, and that is the correct answer. Okay, C is the correct answer. So when we have a confidence interval, we're saying that the likelihood that any confidence interval, because if you can make as many confidence intervals as you want on samples of 4,000 graduates, will contain the population mean is 0.95, or a 95% probability that if you make a confidence interval based on 400 graduates, the probability that confidence interval will contain the population mean is 0.95. Okay, D sounds right, and sometimes we treat it like that, but D is not actually correct. Okay, moving on to, let's see here. Question number 18. Knowledge of the population standard deviation and having a sample mean, a 95% confidence interval that the knowing the population standard deviation and having a sample mean. Okay, so we know the population standard deviation and we have a sample mean. A 95% confidence interval infers that the population mean is between 0 and 100? No. Is within plus or minus 1.96 standard deviations of the sample mean? Well, standard deviations, that's talking about the distribution of the population observations. Okay? Standard errors, remember, is what we're talking about with the group means. So is within plus or minus 1.96 standard errors of the sample mean. Okay, so standard errors is the standard deviation of the sampling distribution. So the correct answer is C. And if you don't know the difference between the sampling distribution and a population distribution, make sure you take a look at that. And that's the reason why it's the standard error and not the standard deviation. The standard deviation is I'm talking about the population standard deviation or population distribution. Okay, the distribution of the student's t, and I know that this word right here, student's t, is throwing you off. Let's just go with the t distribution, because that's what I've really been referring to it as. Has a mean of 0 with a standard deviation of 1. A mean of 0 with a standard mean of 0, or a mean of 1 and a standard deviation of 1. No, it doesn't have a mean of 1. It's got a mean of 0. Okay, a mean of 0 and a standard deviation that is dependent on the sample size, or a mean that depends on the sample size. No, because the mean is 1 and a standard deviation of 1. Okay, the answer is C. And the reason why is because the standard deviation depends on the degrees of freedom. Okay, the greater number of degrees of freedom, the smaller the standard deviation is, and the closer and closer it gets to the z score. Okay, so it's the degrees of freedom changes the standard deviations, if you will. Okay, so it's got a mean of 0 and a standard deviation that depends on the sample size. So a random sample of 20 items is selected from a population. When computing a confidence interval for the population mean, what is the number of degrees of freedom that should be used? So degrees of freedom is n minus 1, and so we've got 19. Okay, a random sample of, which if you want to see the formula for degrees of freedom, I put it, let's see here, I put it right here. Degrees of freedom equals n minus 1. Okay, degrees of freedom equals n minus 1. A random sample of 85 supervisors, so we've got a number of 85, revealed that they worked an average of 6.5 years before being promoted. The population standard deviation, so we've got a population standard deviation of 1.7, which means that we can use the z-scores using the 95%, or using the 0.95 degree confidence. What is the confidence interval for the population mean? Okay, so what we're calculating is the confidence interval. Okay, so we've got the population standard deviation, so we have a z statistic. So the formula for the confidence interval is x bar plus or minus z, the standard deviation, over the square root of n. Okay, so let's see here. So you've got the confidence interval right here. We're calculating a confidence interval. x bar plus or minus z with the standard deviation over the square root of n. And so, first of all, x bar, what is x bar? X bar is 6.5. Okay, plus or minus the z-score, so we're going to be using 1.96 for the z-score because we want the 95% confidence interval. Okay, so 6.5 plus or minus 1.96 multiplied by the standard deviation is 1.7 over the square root of 85. Okay, so the reason why we use this formula is, once again, the big reason why we're doing this, we want to determine the confidence interval, and we're using the z-score because we know the population standard deviation. And if you work all of this out, it's going to give you 6.5 plus or minus the margin of error. The margin of error is 0.361. The margin of error is 1.96 multiplied by 1.7 divided by the square root of 85, which gives you 0.361. So it's 6.5 plus or minus 0.361, which will give you the answer of C. So because if you add or if you subtract 0.361 from 6.5, it's going to give you 6.14, and if you add 0.361 to 6.5, it's going to give you 6.86. Okay, a survey of 50 retailers revealed the average price of a microwave is $375 with a sample standard deviation of 20. So we've got a sample standard deviation of 20. When you see sample standard deviation of 20, that means use the t-distribution. Use the t-distribution. Okay? We've got 50 retailers. What's the degrees of freedom? The degrees of freedom is 50 minus 1, which is 49. Okay? So the average price is $375. Assuming the population is normally distributed, what is the 95% confidence interval estimating the true cost of the microwave? So we've got $375 plus or minus, and we're going to go to the t-distribution. Okay? So we find the degrees of freedom in this left-hand column. Degrees of freedom is 49. Okay? And we come over here. Which one of these numbers should we use? 49. We're going to want to do a 95% confidence interval. So we find this is the column for the 95% confidence interval. So it's this column right here, 95% confidence interval. So it's 2.01. 2.01. So it's 375 plus or minus 2.01 multiplied by the standard deviation of the sample, so 20, divided by the square root of the total number. You're not doing the square root of the degrees of freedom, you're doing it by the number of samples, or the number of observations. Okay? So 3.75 plus or minus 2.01 multiplied by 20 divided by the square root of 50. If you do 2.01 multiplied by 20 divided by the square root of 50, it gives you the margin of error. The margin of error is 5.69. So it's 375 plus or minus 5.69. And if you work that out, it's going to give you, what is it going to give you? Well, 375 minus 369.31, then 375 plus 380.69. So there you see the 375 plus or minus 5.69 gives you the 95% confidence interval to estimate the true cost of the microwave. Okay, moving on to the last few questions. Local government officials are interested in knowing if taxpayers are willing to support a school bond initiative that will require an increase in property taxes. Randomly selecting 750 voters, 450 of these voters were in favor of the school bond initiative. The 95% confidence interval for the true proportion of the voters is, so right here, the big thing that you need to look at is we're looking at proportion and we want to know confidence interval. So what is the formula? What is the formula for calculating the confidence interval of a proportion? The confidence interval of a proportion. So we're going to go back up here and we're going to find this right here. The confidence interval of a proportion. So P plus or minus. So what is P? P is the proportion. Okay. So the proportion is 750. Let's see here. 450 divided by 750. Okay. 450 divided by 750. We'll take the calculator out. 450 divided by 750 equals 0.6. So 0.6 is the proportion. And if you look at the confidence interval for the proportion, it's plus or minus. So 0.6 plus or minus the z-score. And the reason why we're using the z-score when we're talking about proportions, we're talking about the population of the proportion. Or the proportion of the population, rather. So plus or minus the z-score, we want a 95% confidence interval, so we do 1.96. So 0.6 plus or minus 1.96 multiplied by the square root of 0.6 multiplied by 1 minus 0.6, which is 0.4, over the total number sampled, which is 750, which if you work all of this out, it gives us 0.6 plus or minus the margin of error, and the margin of error is 0.035. 0.035. So it's 0.6 plus or minus 0.035, which if you add 0.035 to 0.6, it gives you 635. Subtract it, gives you 0.565, which is D. Okay. 24. Survey of an urban university. We've got a population of 25,450, and then showed that 750 of 1,100 students. So they took a sample of 1,100 students, and 750 of those attended the home football game during the season. Okay, so we've got a proportion of 750 over 1100. That's proportion. Using a 99% confidence level interval. So let's find what's the number for that. I've got it right here. 99 is 2.576. Okay, 2.576. So first of all, what is 750 divided by 1100? Let's get the calculator out. $750 divided by 1100 equals 0.68. Okay, and then we've got plus or minus, because we want a confidence interval, so we're going to use the confidence interval for proportions. So let's see here. Confidence interval for proportions. So 0.68 plus or minus, and then the z-score for 99 is 2.576 multiplied by the square root of the proportion. So 0.68 multiplied by 1 minus the proportion. So 1 minus 0.68 is 0.32 over the sample number. So the sample number is 1100. Okay, so if you multiply all this out, it gives you the standard error. So let's figure out the standard error really quick. Let's see here, 24. Let's do 0.68 times 0.32 equals, nope, 0.68 times 0.32. There we go. So it's 2176 divided by 1100. Okay, and then you take the square root of that, and then you multiply that by 2.576. Okay, which will give you 0.0362. Now, normally you would just take this and add it to 0.68 and subtract it from 0.68. But we have an additional piece of information. The population of 25,450. Now that we have this additional piece of information, we can say the population isn't infinite. We can adjust this to reflect the population, and we're going to use the finite adjustment, the finite population correction factor. And you do that by doing the population minus the sample over the population minus 1, and you take the square root of that. So the population of 25,450 minus 1100 over 25,450, and you take the minus 1, you take the square root of that, and it gives you, if you factor all of that out, so if you do the finite population correction factor, you multiply 0.0362 by 0.9782. Okay, which it doesn't change it a whole lot, but it changes it enough to give you the correct answer. So it'll give you the correct answer of C. Okay, and so if you multiply this by this, it will give you the correct answer. Let's see here. 0.0362 multiplied by 0.9782. So the standard error, the margin of error is 0.3544, and so you do 0.68 plus or minus 0.3544. Let me just erase some of the things here. Okay, so 0.362 multiplied by 0.9782, which this is the finite population correction factor, gives you 0.3544, and so you do 0.68 plus or minus 0.3544, and it gives you the answer of C. Okay, a group of statistics students decided to conduct a survey at their university to find the average amount of time students spend studying per week, assuming a population standard deviation of 6 hours. So you've got a population standard deviation. Okay, we need to draw population standard deviation of 6 hours. What is the required sample size? So now we're calculating sample size, which I put on here. So we've got a population standard deviation of 6 hours. So are we using T or are we using Z? The answer is Z, because we have a population standard deviation. Okay, so for sample size, we're using N equals Z multiplied by the standard deviation divided by the margin of error. The margin of error that we're willing to tolerate is a half an hour. So you're like, so do I use 30? What do I use? The answer is you've got 6 hours right here, so you need to use half an hour right here. So if you use 6 for this, you need to use 0.5 right here. Okay? So we have the z-score. Let's see here. Assuming a population standard deviation of 6 hours, what is the required sample size if the error should be less than half an hour with a 95% confidence interval? So we've got 0.5. Okay. Then we've got the standard deviation of 6 hours. Okay. And then we've got the z-score because we want the 95% confidence interval of 1.96 multiplied by 6. Okay, and then you take all of this and you square it. And so 1.96 multiplied by 6 divided by 0.5 squared equals 553.19. And with sample sizes, you always round up, so the correct answer is A. So you want 554 people. Okay. Which of the following is not necessary to determine how large of a sample to select for a population? Okay. So the level of confidence in estimating the population parameter, you definitely need that. The size of the population, do you need to know the size of the population? The maximum allowable error, you definitely need to know that. I mean, really, what you're looking for, okay, to determine how large of a sample size, okay, the level of confidence, you've got right here, the z-score, okay? The maximum allowable error, E, down here, okay? The estimation of the population variance, that's the standard deviation, and so the only one that you don't need is B, okay? Lastly, a sample of 100 is selected from a known population of 350 elements. The population standard deviation is 15. Use a finite correction factor. So we've got a population of 350 elements. The population standard deviation is 15. Using the finite correction factor, and the sample is 100. When you have a sample and you know the population size, you're probably going to need to do a finite correction factor. And then when you know the population standard deviation, that means that you can use the z-score. Okay? So let's do this. What is the standard error? First thing that we need to do, let's find the formula for the standard error. Okay? Standard error of the mean. Standard deviation over the square root of n. What's the standard deviation? We've got 15. What is the sample size? 100. The square root of the sample size is 10. Okay, so let's do this. 15 over the square root of 100. Okay, so in other words, 15 over 10, which is 1.5. Okay, so that's the standard error. Use the finite correction factor. What is it that, which one of these is the standard error of the sample mean using the finite correction factor? Okay, so we need to do n. What is big N? 350 minus 100 over 350 minus 1 and the square root of that. Okay, so if you factor all of this out, let's look at the calculator. Okay, you've got 250 divided by 349. Equals, and then you take the square root of that, which is 0.8463. So you do 1.5 multiplied by 0.8463. 1.26. Okay, 1.2695. So 1.2695. So in short, this is what I want you guys to take away from this. The first thing that you need to do is figure out what question you are answering. Are you looking for the confidence interval? Are you looking for the standard error? Are you looking for the margin of error? Are you looking for the z-value? Are you looking for the probability? Make sure you know what question you're answering. Okay? Next, look for the word population or sample next to the standard deviation. Population or sample next to the standard deviation. I should write this out for you guys. Let's clear this off. Erase all ink. Better yet, I'm gonna give you guys a decision making tree. Okay. Okay. The very first thing that you need to do. What are you solving for? Okay. Once again, confidence interval, standard error, probability. Sorry, give me a second. Probability. Let's see, confidence interval, probability, standard error of the mean, z-value. You've got all these different formulas, and you need to make sure, sample size. You need to make sure that you're solving for the exact correct statistic, if you will. Okay. The next thing that you need to do is, are you working with a binomial or are you working with a continuous? And the way that you're going to know that is if you see the word proportion, then you're going to be working in the proportions area down here. If you see mean, then that means that you're dealing with something that's continuous. And you're either going to use the t or the z distribution. Okay. After that, look for, do you know the population standard deviation or do you not know the population standard deviation? If you know the population standard deviation, then you use the z distribution. If you do not know the population standard deviation, use the t distribution. Okay? So that's really what you guys need to know. Do you know the population and if you know the population standard deviation, use, if yes, use the z. If no, use the t. Okay, so this is what you need to look for. Are you solving for the proportion or the mean, which is continuous? Discrete or binomial, use the proportion, so on and so forth. Hopefully this was beneficial. I hope that you guys do amazing on the test tomorrow. Yeah, guess I'll talk to you later.